Most of the time in chemistry, we have normal chemical reactions. But now in this unit, we're going to switch and talk about nuclear reactions. So, what do you think? Which releases more energy, chemical reactions or nuclear reactions? You're right. It is nuclear reactions. So, this is a picture of the Nagasaki bomb that was dropped during World War II. So, what causes these nuclear reactions? Well, you need radioactive nuclei. So, what a radioactive atom or nuclei is it is an atom that is unstable. And the reason why it's unstable is it could just be too big, could have too many protons, too many neutrons in that nucleus, or maybe it doesn't have enough neutrons, or maybe it has too many neutrons. Um, so these are some of the reasons why it will fling out particles from the nucleus. So and that's a little bit different. So in a normal chemical reactions, the nucleus is not used. It's just the electrons that are doing the reacting. But in a nuclear reaction, you have particles that are being flung out from the nucleus. All right, so what makes some nuclei stable and others radioactive? It all has to do with the binding energy. So in that nucleus, it is held together through what is something called binding energy. And looking at this chart, graphing binding energy versus the mass number, we see that iron has a special stability. Um, it's a very, very stable element because it has a lot of binding energy. And again, to separate out your nucleus, you're going to have to break that binding energy. So the higher the binding energy, then the more stable the nucleus is. And we already answered that question. Which element is the most stable? It would be iron. When you look on the periodic table and you see the average atomic mass with a parenthesis, this is a clue that that element is radioactive. So, and you can see in your periodic table that a lot of these heavier elements, um, that they're very radioactive. So 84 and higher is radioactive. And there's some anomalies, like we have tactinium right here. For whatever reason, nature doesn't like to make this element, so this is a man-made element, and it is radioactive. As soon as it is made, then it decays and becomes something else. This is a chart that shows what's called the band of stability. So it is graphing the protons versus the neutrons. And we see that up until about element 20, having equal number of neutrons to protons, that's pretty stable. But then you see past element 20, when it gets large enough, it needs more neutrons. So we see that more and more neutrons are required in that nucleus to be stable. What happens if you're not in this band of stability? Well, then the nucleus is going to fling out a particle to try to make it more stable. So if you're in this region, beta decay occurs. So this means that we have too many neutrons, not enough protons. If you're in this region, this means you have too many protons or not enough neutrons. And so it will fling out either a positron, which is a beta plus decay, or it could even capture its own electron and drag it into the nucleus. Um, those elements, I've already mentioned this, past 83 or 84 and above, they are unstable because they're just too darn big. So they have too many protons, too many neutrons, and so they will decay through what's called something, it's called alpha decay. All right, so let's look at nuclear reactions. So the types of nuclear reactions that we're going to talk about are alpha particles, beta particles, both beta negative and beta positive, and also gamma rays. And whenever there is an unstable nucleus, there will be usually a combination of these. So let's start off with alpha particles. So what is an alpha particle? It is a small piece of the nucleus. It looks like, smells like, tastes like, is what I say, a helium nucleus. So the symbol of your alpha particle is the symbol of helium, and then we have the mass is 4 and our proton number is 2. So really what this looks like it looks like two protons and two neutrons. And this gets flung out of the nucleus and it doesn't travel very far and it's really slow moving and it's quite heavy because it's so large. You could hold out your hand and you could stop an alpha particle. And so, as far as causing damage or radiation from alpha particles, not too much worry here. They really don't travel very far, so it's not like they'll travel miles and miles. I mean, we're talking about inches. So, and your skin will stop it. Even a piece of paper would stop an alpha particle. The reason why it doesn't travel very far is because it is positively charged. It will gather electrons just from the air that's around it, and it will turn into harmless helium gas. These alpha particles, however, can cause a lot of damage if they're inside your body. Because they're so large and slow moving, if you were to eat something that emitted alpha particles, it possibly could knock atoms out of molecules and damaging maybe DNA of the cell and cause cancer. So these are really, really bad if they're inside a living organism. Let's look at our next particle. Our next particle is beta particles. Now, if you're just told beta particle, you need to assume that it's a beta minus particle. And so the beta minus particle looks like, smells like, tastes like an electron that gets flung out of the nucleus. And so when you write this, the mass of an electron, it does have a mass, but it's so small compared to protons and neutrons, we say it has a mass of 0. So that's where that 0 comes from. And it does have a charge of a -1. And if you use this symbol here, it'll help you with your nuclear equations that we're going to talk about in just a minute. If it's a beta plus, then you'll draw it like this. So this is a particle called a positron. So it's the same size as an electron, but it has a positive charge. So, and it's an antimatter particle, and it's more physics, and we're really not going to go into it. All you really need to know is how to draw a beta plus. You will do 0 plus 1e. So these beta particles, let's talk about them. So they are fast moving, a lot faster than your alpha particles, and they can penetrate your skin, but they can be stopped with plastics and metals. And this is not as damaging inside the body. And so if you were to eat something that was a beta emitter, it would just pass out of your body and hopefully not hit too many molecules that could knock the DNA and mess with it. Excuse me. And these are the these beta emitters. These are used a lot in treating certain cancers because they can be targeted at the cancer and they can penetrate the skin and target the rapidly growing cells of the cancer. All right, let's look at gamma radiation. So gamma radiation is a high energy wave or photon. Concrete and lead, and quite a thickness of them, will reduce their strength. And if it's thick enough, you can stop it, but it really has to be pretty thick to stop this gamma radiation. And this is the radiation that travels over long distances. When I was a little girl, the threat of nuclear war was always hanging over our head with the Cold War in the 80s and the 90s, and they had some TV programs that they talk about a bomb going off in a major city and everybody dying of this radiation poisoning. And it's this gamma radiation that causes that. Because it's such high energy, it can disrupt cell division. It can cause you to have what's radiation sickness, so you'll throw up and have diarrhea, not very pleasant, and you can die from this. So, and a lot of the radiation that we talk about, gamma waves are also let out with them, um, but something large like a nuclear bomb would send out a lot of gamma radiation. And here's a little diagram that just kind of shows you the penetration power. So alpha, again, your skin or a piece of paper. Beta can travel a couple inches through. your body, so that's why it's showing passing through your hand. Um, so a thicker sheet of aluminum could stop that. Gamma radiation, X-rays, they've thrown that into. You need something that's a little bit thicker. And we didn't talk about neutrons, but these are the furthest penetrating particle that there is. And we're going to talk about some uh, equations, and I'm really not going to give you any neutron equations. So let's look at a diagram, and this is representing a magnetic field. So you have your radioactive source, and let's start with alpha particle. So as the alpha particle comes out, it is very heavy, and it is positively charged, and it is slightly influenced by that negative field. So this is our alpha particle, or it's drawn like this, and it is positively charged, and it's very, very heavy. Let's look at the beta minus. So your beta minus, its mass is not so great, and so because of that, it is affected quite radically by a magnetic field. And your positron, or your beta plus, would just go in the opposite direction. So it looks like this. And the very last particle to look at would be gamma. And gamma doesn't have a positive or a negative charge, and so it'll just zip right on through. So again, that's our gamma. All right, so let's look at solving problems in nuclear decay. So a lot of your radioactive nuclei, they'll go through what's called a decay series. So it might fling out an alpha particle, then a beta, then a beta, then an alpha particle, and it might do it quite quickly or very, very slowly. And here is a radioactive decay series for uranium-238. And so eventually you see that the nucleus keeps flinging out particles until it's stable. And where is it most stable? With lead 206. So this is a decay series of uranium-238. Let's talk about some nuclear equations. So starting with that uranium-238, it flings out an alpha particle. That's the first part of its decay series. So we can see the particle getting flung out right here. This is an alpha particle right here that gets flung out. So remember, it's a helium nucleus, 42He. And then you have the leftover. And this is called the daughter nuclide. And what I want you to notice is there's a conservation of mass that's going on here. So whatever the numbers are on the left-hand side, they have to add up and equal the ones on the right-hand side. So if you know a helium nucleus comes out, you're told it's alpha decay, then you know you need to take 238 minus 4, and you'll get 234. And down here, again, this is the proton number or the atomic number. So on this side, it's 92. If it flings out a helium nucleus, so we have two particles that left, what's the leftover? Well, we have 90. So, and then you look on your periodic table to figure out what this element is. So again, look on your periodic table and look at number 90. And so you can write the symbol. And this symbol is thorium, so TH. So again, the numbers must balance both the top and the bottom rows. And so I will always tell you what particle is going to be flung out of the nucleus. And so you just have to know how to write the leftover. So let's have you practice this. Looking at that last example, go ahead and write and finish the equations here for alpha emission. So the very first thing that you're going to do is it's going to fling out an alpha particle. So 42He, and this will happen with each one of these. So go ahead and practice what the leftover will be. So remember, the top and the bottom rows have to match. And use that bottom number and look in your periodic table and look up what the symbol of that element is. So go ahead and stop the video and see if you can figure out what the three leftover daughter nuclides are. Okay, we're back. Let's see how you did. All right, so there's the first one, the second one, and the third one. So let's look at our next decaying particle, beta minus emission. So if it just says beta decay, always assume it's beta minus. And so that is an electron that gets flung out of the nucleus. And what ends up happening is a neutron changes to a proton. So this helps the atom become a little bit more stable. And let's look at this first one. So we have thorium-234. The beta particle is going to come out of its nucleus. And what is the leftover? So we have 234 minus 0 would be 234. And then notice this is a negative number, so don't get confused here. But you actually are going to have 91 be your leftover. Why? Because 91 minus 1 gives me 90. So you have to have the bottom rows match. And then I look up 91 and I find it is, I think it is Pa. Okay, let's do the next one. So we have calcium 14 and it is flinging out a beta minus particle. So I end up having 14. And what would be the proton number? It would be 7, and that is nitrogen. So 7 minus 1 is 6. So this one is a little bit tricky because of the negative number, but it's done the same way as just that alpha particle emission. You still have to have the top rows match and the bottom rows match. So we have 234 equals 234, and we have 91 minus 1 equals 90. And then we have our 14 and 0 equals 14, and 7 minus 1 equals 6. So just double check these when you do them. Oh, and I did get the Pa right, so yay me. All right, let's look at beta plus. So this is a positron. So it's a particle that looks like an electron, except for it's positively charged. So let's go ahead and look at that. So we need to figure out the leftover particle. So when this positron gets flung out, what happens is a proton ends up changing to a neutron. It just changes the ratio of neutrons and protons. Excuse me. It changes the ratio of neutrons and protons and makes it more stable. So again, we have 22 minus 0, so we have 22 is our leftover, and then we have 11, and now this is a 1, so we're going to go to 10. So this one is going to be neon. All right, so just double check here. So you have 22 on top, 22 here. You have 10 plus 1 here, and you have 11. All right, let's go to the next one. So we have, again, we have our unstable nucleus. So this is nitrogen 13, and it's going to fling out a positron, and I'm going to have 13 as my top number, and my bottom number I will have 6. And when you look at what 6 for the atomic number is, that would be carbon. And then just double check. So we have 13 plus 0 is 13, and we have 6 plus 1, that would be 7. So beta plus. Let's look at electron capture or K capture. So this is a little bit different. So the nucleus will actually reach out and grab an inner electron. And they used to call it the inner shell the K shell, so that's why they call it K capture. So, but it's just called electron capture. So this one's a little bit different in that you are going to see the electron on the left-hand side, so before the arrow. So that's a big clue that you have electron capture if your electron symbol is a reactant and not a product. But it's done the exact same way as far as balancing. You want to make sure that the top row equals on each side and then the bottom row. And look, there's a little negative number again, so watch out for that. So 47 minus 1, we do get 6, or 46. Gamma emission, it usually follows other types of decay, and it really doesn't change your formula at all. I mean, I could tack on gamma here, and it doesn't have a mass, and it doesn't have any protons or anything like that. So it's often written like this with the little gamma symbol and the 2 zeros. Now, what we've been talking about are transmutations. where one element becomes another, and it's nuclear chemistry, where we're changing the nucleus, and if the proton number changes, then we have changed it to a different element, and that's called a transmutation.